Greetings to all. My name is Rašjl, and I was responsible for activities within Work Package 7 of MIT project. I'm from University of Zagreb, Faculty of Electrical Engineering, or in short UNIZEG-FER, from Croatia, and our core team consisted, beside me, two young researchers, Sara Raus and Josipa Hranić. We have also included several other professors from the same faculty that were mainly involved for consulting, verification, and validation purposes and activities. Now I will present our main achievement that is made in scope of this Work Package 7, and that is new support tool for decision makers, mainly future investors. On this slide, you can find my email for any question that you will that will arise in future. And also you have a link to standalone, currently available standalone DMT version. So, as power system experts in this quite multidisciplinary project, we had to ask ourselves why to go into geothermal energy exploitation. And there are numerous reasons for this. It is a form of renewable energy source that has stable and dispatchable power output in comparison, for example, to wind and solar power plants. It is also attributed with negligible or zero greenhouse gas emissions, and as one of sustainable energy sources. In perspective of EGS, it is applicable to almost every country in the world. And it is also almost inexhaustible energy source that will exist as long as Earth exists. In addition, it can be used for multiple purposes, such as direct heating or cooling applications, electricity production, or both in generation applications. Although it was said previously that EGS systems are applicable to almost every country in the world, a certain site-specific preconditions have to be present for successful EGS project implementation. First of all, a large permeable reservoir containing large enough amount of heat resource is of course needed. Also, water as medium for heat transfer is necessary, same as overlaying layer of impervious rock. Also, there should exist injection and extraction wells that will form a reliable recharge mechanism. EGS project, same as every other geothermal energy utilization project, is extremely interdisciplinary in its nature, especially in comparison to other types of power plants. So, expertise from geologists and mechanical engineers is prerequisite to find, locate, explore, and in some cases stimulate potential EGS sites or geological settings. It is also necessary to properly model geothermal heat reservoir, for which thermodynamic expertise is also needed. Once geothermal energy reaches surface, expertise from electrotechnical, mechanical, power system, and thermodynamic spheres is crucial to properly design and install surface facility for geothermal energy conversion to certain form of useful energy source, such as electricity or heat or both. In that sense, useful energy source that can be satisfied by extracted geothermal heat energy largely depends, of course, on its temperature, or of temperature of provided geothermal heat. A Lindahl diagram, of which one type is depicted on this slide, shows a correlation between potential geothermal energy application and geothermal brine temperature. And starting from lowest temperatures and going up to the highest temperatures of geothermal brine, one can use it, for example, for aquaculture, swimming pools, heating, greenhouses, space heating, and others. And somewhere around 130 Celsius degrees starts option for application for traditional geothermal electricity generation. The higher temperature of geothermal fluid is, the more electricity can be produced, and you can use a wider range of available techniques. But EGS aims to produce electricity with temperatures of geothermal brine well below already stated 130 Celsius degrees. Once identified potential site for EGS project implementation doesn't mean it will be really implemented in reality, in practice. Namely, there are potential numerous issues with EGS implementation on real site. First of all, brine can have too low temperature for energy needs in surrounding, and even if brine has high enough temperature, potential users such as power grid or heat demand pipelines and associated grid can be too far from this site, and additionally, brine can be contaminated with some radionuclides, or its content can have significant potential for scaling and corrosion. Special attention should be also focused to nearby settlements and related social acceptance of these projects, especially regarding potential induced seismicity during process of drilling or fracturing. As you can see on this slide, basically there are 5 main stages in EGS project implementation. First stage is permitting phase, where certain permits for exploration and drilling should be obtained. Second phase includes exploration of potential site, including, let's say, low capital exploration drilling and stimulation, also obtaining additional permits for utilization, installation of field gathering system and others permits. Next phase is actual drilling in full necessary diameter, additional stimulation, complete development of installation of gathering system and installation of geothermal pumps. Fourth phase is power plant construction that includes both power plant and transmission line constructions. Last phase is, of course, power plant operation with all necessary activities necessary or needed for proper power plant operation. Of course, each of previously mentioned EGS development stages involves certain amount of investment or related costs. How do you want better to whatever you want better to hear. During exploration and permitting, costs can be divided in those related to test drilling and those for permitting and leasing. When project comes to next phase, there are additional costs related to full diameter drilling and necessary stimulation, and also for obtaining further permits for upcoming activities. At the end, real equipment has to be purchased and installed, so you need to buy that equipment. Therefore, there are costs related to gathering system installation and those related to power plant engineering, permitting, and finally installation. As it can be seen on previous 2 slides, development of EGS projects is very complex with associated significant costs in each development stage. And therefore, decision makers, mainly investors, need some sort of support when making decisions. And possible solution for our aforementioned issues is proposed decision-making tool that was developed within work package 7 of this MIT project. As it is capable of evaluating different geothermal energy transformation techniques, such as transformation to only heat, only electricity, or combined heat and electricity needs. It is modeled in such a way that enables taking into account technical, economic, environmental, and societal aspects while deciding on EGS project implementation. Based on output results, one can get info or clue on best way how to utilize available geothermal potential. It also integrates multi-criteria decision-making, or in short MCDM module, which enables grading of different application options. We will talk more about MCDM in next slides. This slide depicts first version of DMT concept and its main features that it should encompass. When comparing developed DMT and this first sketch that it was made 3 and even more years ago, we as developers are very happy that our first concept was quite similar to final concept that is actually integrated in DMT. Decision maker should gather all relevant data and input it into DMT through modeled interface. This data, among others, relates to technology details, environmental aspects, certain kind of forecasts, prices, demand, or something else, expected heat or electricity needs in surrounding, and on any other input. In order to get useful output data to user and provide it to user, DMT has plenty integrated functions that are also integrated into user-friendly application. And as previously said, one of major integrated modules is MCDM module that help users to get clue on best option for utilization of available geothermal energy on site. Previously described concept and approach in modeling and development of DMT has anticipated satisfactory level of support needed for investors or other users that seek for certain answers, mostly financial in nature, and for specific site and for different geothermal energy utilization on that site. And therefore, it integrates technical, economic, environmental, and societal aspects of geothermal projects, and as such, can serve as foundation for comprehensive assessment of EGS project. And main outputs that can be of interest for users are internal rate of return, levelized cost of energy, either electricity or heat or both, and net present value of project. Of course, there are a large number of input parameters within DMT, and for those that can be directly or exactly monetarized, the user have two options: either to use default values in software, in application, or to use their specified values. There are, of course, a large number, larger than the number of these factors that can be monetized, so large number of input parameters that are very hard or even impossible to monetize, such as social acceptance, environmental aspects, and other. And these parameters are accounted and processed by that important, already mentioned, MCDM module of DMT that actually enables comparison between several approaches and or different sites. Within this model, user can specify its subjective attitudes towards specific parameters or group of parameters by defining and putting different or inputting different weights to some of them. It has to be noted that DMT does not take into account model of geothermal reservoir or any other subsurface phenomena. Therefore, focus is switched from modeling and exploring geothermal potential in different locations to modeling above surface phenomena. So Bianca in last presentation, in last presentation that was made, we also already seen that there are some surface and subsurface phenomena. Here we are focused on above surface phenomena or surface phenomena. And the behind logic is that in this way it is possible to better assess energy transfer from its geothermal source to final users. Model is developed in well-known MATLAB software, and at the moment, as I already said at the beginning, standalone executable application is available for any user. Once dissemination process through a concrete PhD thesis related to this DMT is finished, an open code MATLAB version of tool will be also provided to scientific public or any other interested sort of public for further research and upgrade. As already mentioned, There are modeled several arrangements or modes of utilizing geothermal energy potential in scope of DMT, namely 4 of them. First mode is depicted on this slide and relates to only heat mode, where whole energy potential is transformed for useful heat in this slide, for example, for heating homes. Second mode is depicted on this slide and relates to only electricity mode, where whole geothermal potential is transformed to produce electricity, mainly by application of mobile or standalone ORC models that Rašjl elaborated earlier. Binary type of geothermal power plant is assumed in this model. Third mode is depicted on this slide and relates to first kind of combined heat and electricity production, and it is so-called topping mode. There is also bottoming mode, but it is not modeled because it is rarely used. Part of geothermal energy in this mode, geothermal energy potential, is transformed in electricity, and the rest of available energy is transformed to usually low temperature heat demand. So this is combined heat and electricity in series. Apart from this, we have also fourth mode, where we have combined heat electricity production in parallel. Here, total energy, geothermal energy potential, is partly transformed in electricity, and the rest of available energy, geothermal energy, is transformed to here usually medium to high temperature heat demand. As previously mentioned, DMT is modeled in MATLAB software with plenty integrated functions that mutually shares and process data. And in addition, DMT is made as user-friendly application, as can be seen on this slide. First type in this application provides basic information and some guidelines regarding usage of DMT. And regarding other tabs, there are 2 tabs related to results. A tab where scenarios are defined, a tab that enables data input to DMT, MCDM model tab, and tab for oil to water conversion, which is last integrated DMT model, and that will be elaborated at the end of this presentation. These slides depicts user interface, or something that you will see when you select scenario definition tab. Here, user can define basic properties for different scenarios, such as, for example, name and short description of project, expected lifetime of project, and duration of each crucial phase of EGS project implementation. As there are as well other options that can be used to better define each scenario, such as geographical features of site of interest and many others. These slides depicts user interface when you select tab input parameters. All input parameters are divided, as you can see, in 8 different categories, and this enables detailed description of EGS project features. In this way, user can define geological features related to the site, geothermal fluid properties, modes of geothermal energy transformation, so only electricity, only heat, or both, power plant features, data related to used technology, and of course related financial parameters and environmental aspects related to the site of interest. In general, energy-related project, and especially more specifically EGS projects, involves numerous issues and uncertainties during phase of planning and their commission. For example, it is hard to accomplish balanced techno-socio-economic evaluation, and that is due to many conflicting criteria and their interaction. Therefore, in practice, rational decision-making in energy projects is usually very difficult and complex. And in this context, a multi-criteria decision analysis, or MCDA, can be of great importance. it actually represents operational evaluation and decision support approach that is suitable for addressing complex problems that are featured with high uncertainty, conflicting objectives, different forms of data and information, and, for example, multi-interests from or many few different interests from the perspective of users. MCDM model, already mentioned and already quite elaborated, is based on an MCDA approach, and it is integrated in our decision-making tool and has defined 28 criterions used for final grading of each defined scenario or option for geothermal energy potential transformation. So you can see on this slide all of these 28 criterions that are grouped into 5 main sets or groups, as can be also seen on this slide. So those groups are geological settings, technology, economy/finance, society, and last one, environment. For each criterion, a lower and upper threshold are defined based on either relevant expert information or literature review. Same as ranges of criterion values for different grades, same as, so there are also ranges for criterion values that are for which different grades are declared. And based on the grades of all criterions and groups of criterions, final grade of project scenario is evaluated. Due to the fact that not every investor or user has same objective attitudes, analytic hierarchy process or AHP approach is also of great interest in this project. In this approach, AHP actually provides objective mathematics to process these inevitable subjective perspectives and preferences. It is actually synthesizing criteria method that calculates a ratio scaled importance of alternatives through pairwise comparison of criteria, subcriteria, and alternatives. AHP is one of the decision-making processes that decompose a complex problem into a hierarchical order. In other words, the simplest structure of decision problem is a hierarchy consisting of 3 to 4 levels, as shown in the figure on the left. The goal of decision is at the top level, followed by second level consisting of the criteria that are major factors controlling the goal. Then the third level represents the subcriteria of each major criterion, by which the alternatives located in the fourth or third level will be evaluated. After defining the hierarchical levels, next step is creating judgment matrix seen on top right. Once defined, these judgment matrices or pairwise comparison matrices, better said, are used to calculate the local priorities that express the relative impact of the set of criterion on a criterion in that level. For the purpose of enhancing quality and confidence of DMT results, special AHP-based case study was conducted. Previously mentioned 28 criterions from MCDM model and 3 different alternatives of using geothermal energy, so only heat, only energy, only electricity, or both in combined mode, were integrated into Excel document for AHP survey. This document was delivered to examinees from different areas or point of view, and those are industry, educational institutions, research and technology organizations, small and medium-sized enterprises, local community, and the rest. There are some other groups that are put together as other, and we get 37 responses. Based on 37 responses of AHP case study, with 34 responses with confidence ratio less than 15%. Those 34 analyzed or 34 responses were analyzed, and following results were were calculated and are shown on this slide. For industry, for example, for industry sector, for example, most important are economic criteria, as it can be seen. For educational institutions, on the other side, geological criterions were most important, same as for research and technology organization and small and medium enterprises. As expected, for local community, most important criteria are related to environment. In this slide, a glimpse into DMT is shown. Namely, the slide shows a sub-application that encompasses a model to calculate the installed capacity of power plant, heating plant, or cogeneration plant, which depends on chosen option by user. This could be named the core model of DMT itself. It is a connection between users' input data related to geological settings, geofluid properties, and all others, and costs which are based on the calculated installed capacity, which consequently influence the final results related to performance metrics such as energy produced, both electricity and heat, CO2 emissions saved, etc. And also some economic metrics such as net present value, LCOE, project cash flow, and others. In this slide, economic parameters are presented as they are displayed in the DMT interface. As it can be seen, it's very user-friendly and visually appealing. Electricity price, monthly or yearly values, in case of only electricity production and cogeneration. Heat prices, monthly or yearly, in case of heat production and cogeneration. And you can see also project cash flow through all development phases. There are a lot of other factors such as NPV, internal rate of return, and so on that can be accessed via this tab. As already mentioned at the beginning, besides our activity in scope of Work Package 7, we were also involved in activities and deliverables in scope of Work Package 4, where our task was to evaluate techno-economic feasibility of transforming existing oil fields that are at the end or near the end of their lifetime into geothermal assets, in short, oil to water. Eric talked more about this. In this context, several different options or alternatives of available geothermal energy conversion were compared. Additionally, petroleum assets that were converted to geothermal assets were also compared. Major benefits of this approach that Eric also mentioned are use of already developed hydrocarbon reservoirs with high temperature and water cut, avoiding the capital cost by using existing infrastructure, and avoiding the cost of decommissioning of oil or gas wells. For this purpose, additional module in DMT was also developed together with associated methodology and scenario analysis executed in MS Excel program software. Again, huge number of new input parameters were identified as necessary for this oil to water conversion. Some of them are properties of geothermal fluid or reservoir, geographical location of the examined wells, as well as availability of demand for heat or electricity in nearby surroundings. Costs related to investment or capex and operation or opex are also taken into account. For this purpose also, emission factors for each EU country were obtained, and in this way avoided CO2 emissions. It is possible to calculate these avoided CO2 emissions based on share of each fossil fuel in total fossil fuel generation for each EU country. And main results of oil to water conversion methodology were production quantities of both heat, energy, and electricity, economic parameters such levelized cost of electricity and levelized cost of heat, net present value, and associated cash flow. As already mentioned, based on obtained emission factor, it was also possible to evaluate carbon intensity decline in different oil to water scenarios. This slide also presents going from top to bottom, assumed scenarios of converting oil well at the end, going from the most optimistic, that is plug wells and abandoned facilities, to the most optimistic, that is electricity and or heat production. Thank you for your time. I hope I was clear enough, and now I'm ready for your questions.